Hi there, welcome to this video on 3 ways to solve exponential and logarithmic equations. I've titled the 3 ways match, invert, and convert. I'll go over many examples of each type with you, but in this video I'm going to focus on only the simplest examples of each type so you can get the general idea of each approach, and then we'll do more videos in the series on more tricky problems or more involved, interesting problems. So let's get started. The first example here, where it says match bases, I just want to point out to you that match bases is not the directions for this problem. It's actually the type of problem. We're actually doing the directions that you would see on a problem on a test or in a homework assignment would be to solve, and that means to isolate x, to find out what the value of x is. So when we're talking about matching bases, it's because this type of problem works really well with matching bases. So what you notice is that the x is in the exponent. So I need to release that exponent, or release x out of the exponent position. And one way I can do that is to rewrite the right side of the equation as an exponential expression with the base of 2. So let's do that. Let me show you what I mean. Okay, so 8 can be expressed as 2 to the power of 3. So now I have two exponential expressions equal to each other. They each have the base of 2, which means their exponents must be also equal. And then we get our answer. Then we can check this so that we can understand if this makes sense. So in our original equation, 2 to the power of x is supposed to equal 8. And we've said that x is equal to 3. So let's plug in 3 for x, and notice that we do get 8 equals 8, right? So this is the correct answer. So that's the first type, that's matching bases. Let's go on and see another type of equation where we would match exponents. So we're still in the matching category, but this one's a little different. You see that x is to the power of 2 here, and we're saying that it's equal to 8. Now, there's actually a typo here. I'd prefer this to be x to the power of 3 is equal to 8. So let's solve that. Now, you might be able to guess, because you know that 2 to the power of 3 is 8, so you can guess that x equals 2. But we're going to do it more formally so that when it comes to more complex problems, you can still use this approach effectively, even if you can't guess the answer just by looking at it. All right, so yeah, I want that to be a power of 3. And so we have x to the power of 3 equals 8, which we can express as 2 to the power of 3, which is nice because now the exponents match, which means that the bases must match. And of course, you can check that by taking the original x to the power of 3 equals 8, and then replacing the x with the 2, and you get 8 equals 8. Right, so that's matching bases or matching exponents. So we've done both types. Now we also have the type of problem where you use inversion. So to explain this, recall that using inverse operations to solve for x is something you've done in the past with something more simple like 2x plus 1 equals 7. So what would you do to get x by itself here? We would do inverse operations, and when we say inverse operations, we mean operations that would undo the mathematical operations that have already been done. So what's been done to x? Well, it's been multiplied by 2, and it's had then 1 added to it, and we're going to undo those in reverse order. So the first thing we're going to do is subtract 1, because when you add 1, the opposite of adding is subtraction, and when you subtract 1 from both sides, everything stays equal. Then you get the additive identity 0, so that it simplifies to 2x equals 7 minus 1 is 6. And then of course we want to undo the multiplication of 2, and the inverse operation of multiplication is, of course, division. And notice that when we do 2 divided by 2, we get the multiplicative identity of 1, then 1 times x is just x, and that gives us x equals 3. Right, so you've seen this type of problem many times in the past, most likely. If you're working on problems like these, it's because you've already mastered problems like those. Now we're going to apply something similar to answer this question. X to the power of 2/5 equals 16. Now, to get x equals a value, which is our goal because we're solving, so we know we're trying to get x equals something, some simple number. Well, right now, x has a power of 2/5 on it. And what I want is a power of 1, like I have here. So to get a power of 1, I can use some exponent rules along with a property that says if you take a fraction and multiply it by its reciprocal, you get 1. And when the exponent rules that I want to use here are that some base to the power of m, and then that all raised to the power of n is equal to that base, and then you multiply the exponents. So combining these two properties, I can get x released from that power of 2/5. So let me show you how to do that in action. I can't erase that for some reason. Okay. But I want to erase it. I really want to. Well, I can't. I don't know why. This is a new app for me. So we're just going to leave it there and I'll work on for here. So what we have is x to the 2/5 equals 16. And I want to raise that to the power of 5/2 so that I get a power of 1 on x. And to keep everything equal, I'm going to have to also do that on this side of the equation. Then on the left-hand side, I get x to the power of 1. On the right-hand side, I can rewrite 16 to the power of 5/2 using radicals. So this might also require some review depending on when the last time you've seen something like this is. When you have a fractional exponent, the bottom part of it becomes the index of a radical if you want to write it in radical form. And the top part of the fractional exponent can either be put underneath the radical as a power on the base, like this, or equivalently, you can have the radical and the base, and then the 5 power on the outside, and that is actually the way we want to do this because the second root of 16, or in other words, the square root of 16, is just 4, so it simplifies to 4 to the power 5, which is 1024. So that's our value of x there, bringing this down. And you can, of course, check this. Let me do my color swap here. So you can, of course, check this by taking the original x to the power of 2/5 equals 16 and replacing the x with 1024. And then in your calculator, it's very easy to do a fractional exponent if you use the caret key for the exponent, then parentheses for the fraction, 2 divided by 5, and that does come out to be 16. All right, so the next type of example in here, which I need to stop writing on my thingy here. There we go. All right, so the next example here is, or the next type of problem to work on is conversion, which works really well when you have logarithms because most of the time we understand exponential form better than we understand logarithmic form. But logarithmic form and exponential form are inverse forms of each other, which I could go into more explanation, but to keep this video manageable, I advise you to look back at the videos I've done on logarithms and exponentials. Inverse functions also, really good ones to look at. But assuming you understand the relationship between logarithmic equations and exponential equations, let's go ahead and convert this equation log base 2 of x. We're going to convert that to exponential form. So what we want to do is notice that the base of the logarithm is 2. So that will be the base of our exponential equation. So we're going to have something as the power on that base, and then we're going to have something on the opposite side that it's equal to. And it's really easy to convert logarithms to exponentials or vice versa because the base does always stay the same. And then the other two parts of the logarithm, such as the argument, the part that's, it's log base 2 of x, so the thing that's being taken the log of x here, which we call the argument, and the part that's opposite the equal sign, on the other side of the equal sign, those two things basically are going to swap sides. They just switch positions, basically. So the 3 that was on its own is now going to be paired up with the base of 2. That'll be the exponent now. And the x will be on the opposite side of the equals, which is great because x is alone now. And we know what 2 to the power of 3 is. So we get x equals 8. All right, and then to check this, there's something called the change of base formula, which you can use with your calculator to check your work here. And that is the log base b of something, some argument, can always be figured out using either the log button on your calculator, which is log base 10, or the ln key, which stands for natural log, or log base e. So I'm going to use ln, natural log key. And what you're doing is you're converting the log of any base, which in this case is 2, and we don't have a log base 2 button on our calculators usually. Some calculators that are more advanced have an option to change the base, but assuming that you have a very standard scientific calculator with only a log base 10 key or a log base e key, you would use this formula, and it's really no big deal to use it once you get the hang of it. So the base here on the bottom would be 2, remember B for base, B for bottom, and the argument A would be what we're plugging in for x, which would be the 8 here. And so when you do in your calculator the ln key and then 8, close the parentheses, divide, then the ln key again, and then there'll be parentheses, put in your 2, and close parentheses, then you will get 3 and be very happy about it. So that concludes the examples, the simple examples of each type of ways to solve exponential and logarithmic equations. So I will make more videos on the remaining examples in this printout so that you can learn some of the trickier ones, and hopefully you got a lot out of this video. I hope you did enjoy it, and if you did, please like and share, and I'll look forward to seeing you in the next one. Take care.